Graph neural differential equations offer a novel approach to modeling socioeconomic dynamics, simplifying complex systems into tractable relationships that preserve critical system behaviors while reducing computational demands and model complexity. This framework integrates graph neural networks with differential equations, enabling the capture of nonlinear interactions and temporal dynamics in socioeconomic systems. The proposed method is demonstrated through a case study in Baltimore, Maryland, where it effectively models the interactions between social factors, geography, and external stressors. By representing the city's socioeconomic dynamics as a graph, the model captures the relationships between variables such as poverty rates, crime rates, and population density. The differential equation component then simulates the temporal evolution of these variables, allowing for the forecasting of system behavior under various scenarios. The model's ability to forecast system evolution and aid in resilience planning makes it a valuable tool for policymaking. By analyzing the model's outputs, policymakers can identify potential vulnerabilities and develop targeted interventions to mitigate the effects of external stressors. The framework's flexibility and adaptability also enable its application to various urban contexts, making it a promising approach for understanding and addressing complex socioeconomic challenges. The model's performance is evaluated using metrics such as mean absolute error and mean squared error, demonstrating its ability to accurately capture the dynamics of the socioeconomic system. The case study highlights the potential of graph neural differential equations for modeling complex systems and informing data-driven policy decisions. In complex systems, coarse-grained models often struggle to capture the underlying rules governing individual agent behavior. To address this limitation, new rules must be crafted that match the model's granularity. Equation-based models, EBMs, are commonly used to model aggregated states, but they require careful consideration of the underlying dynamics. Machine learning has emerged as a powerful tool for modeling and scientific discovery in complex systems, with applications accelerating in domains such as finance, healthcare, and real estate. These applications include extracting insights, calibrating mechanistic models, and making predictions. Surrogate models, also known as metamodels, have been proposed to alleviate the bottlenecks of agent-based models, ABMs. These models learn the input-output space of an ABM using techniques such as artificial neural networks, ANNs, and can be used for emulation, sensitivity analysis, and calibration. Machine learning can also be used for equation discovery and closure models. For example, the sparse identification of nonlinear dynamics (SINDY) method constructs a differential equation from a sparse selection of mathematical terms that minimizes a time series reconstruction error. Neural ordinary differential equations, neural ODEs, are another technique that approximates a time series with differential equations using ANNs. This research aims to model spacetime socioeconomic dynamics from a data-driven perspective. The specific contributions include conceptualizing and implementing a scale-agnostic EBM for spacetime socioeconomic systems, pairing an arbitrary coarse-graining procedure with a method to extract an EBM of the system, physics, at that model granularity, and performing this task in a differentiable manner, enabling gradient-based optimization of the coarse-grained EBM. Machine learning-enabled coarse-grained epidemiological modeling approach for urban socioeconomic dynamics is proposed in this research paper. The method represents geographic regions as nodes in a graph, connected by edges that signify migration pathways. Each node contains time-varying states, such as the composition of subpopulations, and features, like distance to the central business district or housing capacity. This graph-based approach is inspired by bathtub-type models, where the quantity of interest is related to inflow, outflow, and capacitance. In this context, nodes represent capacity to house subsets of a population, and edges allow for the flow of subpopulations between them. The model aims to track the flux of subpopulations between nodes over time. The graph is formalized as a set of nodes and edges, with the number of nodes denoted as V equals n. An edge is defined as a pair of nodes, and the adjacency matrix A represents all edges and nodes in the graph. The state vector for each node is denoted as x new, and the feature vector is denoted as y new. Capacitive nodes, representing geographic regions of an urban setting, are connected by migration pathways. These nodes contain time-varying states and features, and the model seeks to track the flux of subpopulations between nodes over time. The mathematics of networked capacitive nodes is well understood in the context of diffusion on a graph and resistive capacitive networks. However, this is not the case for urban socioeconomic dynamics, which lack a fundamental understanding and characterization from a first principles perspective. This knowledge gap motivates the development of novel methodologies, such as the proposed machine learning-enabled coarse-grained epidemiological modeling approach, to better understand and model urban socioeconomic dynamics. This section introduces the neural network architecture and mathematical formulations used in the paper. Artificial neural networks, ANNs, are described as trainable universal function approximators, consisting of interconnected nodes in multiple layers, including input, hidden, and output layers. The process is mathematically represented for a single neuron as a weighted sum of its inputs and applies a nonlinear activation function. A neural network is denoted as NN, X, R_N_X right pointing arrow R_out, representing a complete neural network with a prescribed input-output mapping. Neural ordinary differential equations, neural ODEs, are introduced as a framework for modeling continuous time dynamics of a system using neural networks. A dynamical system is characterized by a time-dependent state vector x, t, element of r_d, with the rate of change of the state defined by a neural network parameterized by theta. The trajectory of the system is obtained by solving the initial value problem, which is computed using a numerical ODE solver. The parameters theta are adjusted to minimize a loss function that quantifies the discrepancy between the model's predictions and the true data. The paper then shifts focus to modeling aggregated population dynamics on a graph. Each node of the graph represents a spatially aggregated portion of a domain, equipped with a notion of population capacity, occupancy rate, and attributes. The concept of pressure is introduced, where subpopulations on the nodes respond to pressure differences on the graph, with populations expected to migrate towards regions of lower pressure. The system state is defined as a set of state variables for each subpopulation on each node. X equals x_new1, x_new2, x_new_n, and the full system feature set is denoted as y equals y_new1, y_new2, y_new_n. The time rate of change of each subpopulation is equal to the net flux into the node, including networked migration and exogenous growth and decay, as represented by equation 8. A novel framework is proposed for coarse-graining agent-based models, ABMs, to simulate complex systems. This approach integrates ABMs with empirical dynamic modeling, enabling the creation of empirical dynamic models, EDMs, that capture system dynamics at various scales. The EDMs are derived from the ABM using a systematic coarse-graining procedure, involving node and edge feature definition, empirical dynamic model structure specification, and parameter optimization. In a case study on population migration in response to flooding in Baltimore, the CHANCEC ABM framework is utilized to simulate space-time socioeconomic dynamics. The CHANCEC model comprises 1220 U.S. Census-derived block groups, each containing a representative property occupied by household agents. The model simulates housing dynamics, including household creation, property vacancy, utility calculations, property matching, and market adjustments. The optimization problem for the EDM is defined as minimizing the error between ABM and EDM outputs, given a dataset of ABM simulation outputs. The optimization process involves tuning EDM parameters to best fit observed data using a gradient-based optimizer, such as ATOM. Critical considerations include graph definition, feature and state specification, and selection of appropriate forms for the pressure response function and edge weight function, which vary depending on the modeling task. The proposed framework enables the creation of EDMs that capture complex system dynamics at various scales, providing a powerful tool for understanding and predicting complex phenomena. Researchers have developed an empirical Bayesian model, EBM, to simulate and predict housing market dynamics in a coastal city, integrating agent-based model, ABM, outputs with empirical data. The ABM, CHANCEC, utilizes a simple avoidance utility to evaluate flood risk in home purchase and relocation decisions. 50 unique 50-year simulations were run, varying initial conditions such as vacancy rate, population growth rate, and building growth rate. These simulations were then divided into training, validation, and test datasets. In the coarse-graining step, the spatial domain was aggregated into 4 zones: urban, suburban, rural, and a placeholder for tracking agents that leave the domain. Agents were classified into low, middle, or high income categories based on their income distribution, reducing the output to 12 degrees of freedom over 50 years with 1-year temporal resolution. The EBM captures the evolution of these aggregated states over time using an ordinary differential equation, ODE, solver. Nodal features include mixture fraction, pressure, and a latent variable, Q, acting as a catch-all feature. The model evolves the states with an ODE solver, allowing for automatic tuning of model parameters to minimize an objective function using a gradient-based optimizer. The problem formulation involves defining nodal features, a surrogate function for pressure, and a scaling function, beta. The EBM integrates these components to simulate and predict housing market dynamics under various climate change and socioeconomic scenarios. This approach aims to provide insights into how different factors influence housing markets and guide policy interventions to mitigate potential negative impacts. The authors introduce a novel simulation framework for urban planning, focusing on population dynamics and migration patterns. This framework is based on a set of aggregation rules for spatial and agent classification, as detailed in Table 1. These rules define how to classify nodes within the city based on distance to the central business district and income levels. To enhance model interpretability, each node's feature vector is explicitly defined as the concatenation of population mixture fraction, nodal, pressure, and an unconstrained latent feature, represented by equation 11. The pressure term, P nu, represents the ratio of housing capacity and population at node nu, defined in equation 12. A scaling function beta is also introduced to normalize input features, defined in equation 13. The authors employ an artificial neural network to model the complex relationships between nodes, using a simple multi-layer perceptron architecture consisting of 3 layers. Model states are updated using a first-order Euler integration scheme, as shown in equation 14. The model is trained using a straightforward approach, with a total of 82 parameters to be optimized. Training involves minimizing the absolute squared error between model outputs and the dataset, with a convergence criterion of reaching a local minimum for at least 500 epochs. The atom optimizer is used with a learning rate of 0.01. And the training history is presented in Figure 3. The performance of the trained model is evaluated using mean absolute percent error, MAPE, and mean absolute error, MAE, metrics, as shown in Table 2. Results demonstrate good agreement between the model outputs and the ground truth data, with a MAPE of around 11% and MAE of approximately 22,000 people. A prototypical experiment is presented, showcasing the dynamics of population migration, with good qualitative agreement between the model outputs and the true behavior of each subpopulation. This experiment highlights the nonlinear dynamics of population migration, revealing that low-income urban inhabitants are most vulnerable to outmigration. Overall, the authors demonstrate the effectiveness of their proposed framework in capturing complex population dynamics and migration patterns, providing a valuable tool for urban planning and policymaking. This page presents the experimental results of a novel graphical neural ode for forecasting socioeconomic dynamics. The EBM achieved a 10.5% mean absolute percentage error and a mean absolute error of 25.1 k people, demonstrating its ability to accurately predict population flux between urban, suburban, and rural nodes. Additionally, the EBM successfully predicted the onset and magnitude of outmigration from Baltimore County, which occurred after a critical point at approximately year 10. The average wall clock simulation time for the trained EBM was 6.1 milliseconds, representing a speedup of a factor of 50K over the ABM. This significant improvement in computational efficiency is crucial for large-scale simulations. The discussion section highlights 2 key concepts: model extensibility and model utility. The EBM-specific functional form restricts its behavior to population flux on a graph, with good qualitative and quantitative performance confirming the appropriateness of these modeling choices. However, the model is readily extensible to handle varying granularity, including the number of nodes, nodal state dimensionality, and nodal features. Depending on the modeling goals, adjusting the model complexity may be necessary to resolve certain phenomena. The EBM did not perform feature selection or search over inductive priors to select the most informative features for the task at hand. Instead, the model relied on a preselected set of features based on domain knowledge. This simplification allowed for a clearer demonstration of the model's capabilities but could potentially limit its predictive power in other contexts. The EBM's ability to capture complex, nonlinear behaviors in population dynamics demonstrates its potential as a tool for understanding and predicting socioeconomic trends. Its extensibility and computational efficiency make it an attractive option for researchers and policymakers seeking to model large-scale socioeconomic systems. The proposed methodology introduces a novel approach to constructing and tuning graph-based neural ordinary differential equations, neural ODEs, for coarse-grained representations of socioeconomic systems. This method integrates machine learning techniques with differential equations, providing a tractable, interpretable, and efficient alternative to traditional high-fidelity agent-based models, ABMs. The model captures essential socioeconomic dynamics on a graph, preserving critical system behaviors while significantly reducing model complexity. In a case study focused on migration under flood aversion in Baltimore, the model demonstrated the ability to reproduce complex socioeconomic dynamics with good qualitative and quantitative agreement. This approach offers several advantages, including computational efficiency, interpretability, extensibility, and differentiability. Computational efficiency is achieved through the reduced dimensionality of the EBM, which translates to faster simulations and enables broader parametric studies and more extensive, what-if, analysis. Interpretability is maintained due to the coarse-grained, equation-based nature of the model, allowing for insights into the underlying mechanisms driving socioeconomic dynamics. The methodology is flexible and can be adapted for various levels of granularity, additional features, and hybridized modeling approaches, making it versatile for different use cases. The differentiable surrogate model opens up possibilities for advanced techniques like optimal control and policy crafting, providing a powerful tool for decision-making in socioeconomic planning and resilience strategies. The utility of the presented method is multifold, including computational speedup, ABM calibration through shared parameterization, hybrid ABM-EBM, and coarse-grained, digital twins of real systems. By integrating machine learning techniques with differential equations, this approach offers a promising alternative to traditional high-fidelity agent-based models, providing a more efficient, interpretable, and adaptable framework for understanding and predicting socioeconomic phenomena. Applying coarse-grained digital twins of actual systems can enhance policymaking, disaster management, and urban planning. In real-world scenarios where high-resolution models are computationally infeasible, the proposed approach demonstrates value in simulating complex socioeconomic phenomena. This methodology facilitates the development of computational frameworks for evaluating urban planning and disaster response strategies, using minimal computational resources. Digital twins serve as proxies for complex systems, integrating domain knowledge to analyze, predict, and inform policy decisions. Key applications include informing evacuation strategies in response to natural disasters and analyzing population growth to support infrastructure planning. Results show that digital twins can efficiently approximate population distributions, even when dealing with coarse-grained input data. Notably, when applying machine learning techniques, this approximation leads to reasonable outcomes with much reduced computational overhead, suggesting suitability for near real-time scenario assessment and optimization. Notably, however, we note assumptions were made that higher granularity model calibration will mitigate large inherent sources of approximation-related variability within regional micro-level frameworks and greater dynamic relationships present from not reducing variance prior across iterative resamplings applied. Although using an adequately implemented form and accurate values by refining dynamic descriptions, more importantly they only estimate parameter probabilities effectively relative, not reduced predictive behavior being necessary results themselves than current fully tested representations show future simulations, thus benefiting understanding time considerations affecting to long. The authors build upon previous works in neural ordinary differential equations, drawing from Chen et al. 21, and Rakakis et al. 22, to establish a foundation for their approach. These foundational works introduced the concept of neural networks as approximate solutions to ordinary differential equations, enabling the modeling of complex dynamic systems. The authors extend this concept by proposing a novel framework that leverages the strengths of both neural networks and ordinary differential equations. This framework, termed Neural Ode, combines the flexibility of neural networks with the interpretability of ordinary differential equations, allowing for the modeling of complex systems with high accuracy and transparency. In Neural Ode, the authors employ a neural network to approximate the derivative of the solution to an ordinary differential equation, which is then used to solve the equation. This approach enables the modeling of nonlinear systems and the handling of complex boundary conditions. The authors demonstrate the effectiveness of Neural Ode through a series of experiments, showcasing its ability to accurately model a range of dynamic systems, including population dynamics and chemical reactions. A key advantage of Neural Ode is its ability to provide interpretable results, allowing researchers to gain insights into the underlying dynamics of the system being modeled. The authors also discuss the limitations of their approach, including the requirement for large amounts of training data and the potential for overfitting. Future work includes extending Neural Ode to handle more complex systems and exploring its applications in real-world domains. The model's performance is exemplified through showcasing the best and worst cases in terms of mean absolute percentage error, MAPE, and mean absolute error, MAE. Figure 6 illustrates Run 1, which yielded a worst-case MAPE of 16.0% and an MAE of 28,800, demonstrating the model's limitations in accurately predicting certain instances. In contrast, Figure 7 depicts Run 38, which achieved a best-case MAE of 14,600 and an MAPE of 9.42%, exemplifying the model's capability to accurately predict certain instances with low error. Figure 8 presents Run 45, which resulted in a worst-case MAE of 38,700 and an MAPE of 13.0%, highlighting the model's vulnerability to high-error instances. These exemplars provide a nuanced understanding of the model's performance, emphasizing the importance of evaluating both MAPE and MAE metrics to gain a comprehensive understanding of the model's strengths and weaknesses. By examining these extremes, researchers can better appreciate the model's predictive capabilities and identify areas for improvement.